Space is supposed to be predictable, cold, mechanical, a place where gravity rules and nothing breaks its rhythm. But in November 2025, something did. 3I-ATLAS, an interstellar visitor barely the size of a mountain, suddenly began accelerating. No jets, no outgassing, no visible reason at all. At the exact same time, the sun erupted in violent flares. Earth's magnetic field trembled, and scientist Stephen Burns muttered a warning. A big wave is coming. 2 events, 1 moment. Is it coincidence or coordination? Comets don't behave like this. They sputter, they tumble, they fade. But this one doesn't. It's smooth, precise, predictable, almost programmed. So tonight, we follow its silent trajectory through the dark to ask one question that could redefine what natural means. If 3I-ATLAS is just a comet like they want us to believe, then why is it acting like a spacecraft that just remembered its mission? If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update, as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Breakthrough Alert. 3I-ATLAS's unexplained thrust. Something is wrong in the outer solar system, and nobody wants to say it out loud yet. In November 2025, astronomers monitoring the interstellar object 3I-ATLAS, also designated C2025N1, noticed something that shouldn't be happening. The object was accelerating, not just moving along its expected trajectory, but actively speeding up in a way that gravity alone couldn't explain. The numbers came from NASA's Jet Propulsion Laboratory Horizon system, the same computational engine that tracks everything from satellites to asteroids with ruthless precision. And those numbers told a story that made physicists uncomfortable. The acceleration broke down into 3 components labelled A1, A2 and A3. Think of these as thrust vectors, directions in which a force is pushing the object. A1 measured approximately 1.662 times 10 to the -6th astronomical units per day squared. That's the radial component, pushing either toward or away from the Sun. A 2 came in at roughly 7.089 times 10 to the -7th astronomical units per day squared, the tangential component, pushing along the direction of travel. A 3, the out-of-plane component, registered as 0, completely, measurably, impossibly 0. To understand why that matters, you need to understand what these numbers represent. When astronomers track comets, they often observe non-gravitational acceleration. Comets are icy bodies that heat up as they approach the Sun, venting gas and dust into space. That venting creates thrust, like a leaky pressure vessel spinning through the void. The jets push the comet off its purely gravitational path. But here's the thing about natural venting from a rotating, irregular chunk of ice and rock. It's messy. Jets fire off in multiple directions. The nucleus spins. The surface is uneven. You get thrust components in all 3 dimensions: radial, tangential, and crucially, out of plane. 3I-ATLAS showed none of that messiness. Its thrust was confined entirely to the orbital plane, as if someone had programmed it to push only in 2 dimensions, ignoring the 3rd completely. Over approximately 20 days, this acceleration translated to a velocity change of about 60 meters per second. That's not a subtle effect. That's real, sustained thrust that should leave visible evidence. But observers searching for that evidence found nothing. No new coma had appeared, no tail streaming behind the object, no jets resolved in high-resolution imaging. The object looked, for all intents and purposes, inert. Its magnitude held steady around 14.7 to 14.9, showing minimal variation. It wasn't brightening like a comet waking up near the Sun. It wasn't fragmenting or shedding material in visible quantities. It was just accelerating, silently and precisely, in a flat plane. Imagine watching a boat move across a lake with no motor, no sails, no oars. The water behind it shows no wake. Yet the boat steadily picks up speed, moving in a perfectly straight line as if guided by invisible rails. You'd have questions, big ones. The central question for 3I-ATLAS is this. If this is just a comet, why is it behaving like a spacecraft? The stakes here reach far beyond one weird rock tumbling through our solar system. If natural explanations fail, if we exhaust every possible mechanism that physics and chemistry can offer, then we're left staring at two possibilities. Either we're witnessing some exotic phenomenon that current science doesn't account for, or we're looking at something engineered. Both options rewrite what we thought we knew about interstellar objects. Both options have implications that ripple outward into how we understand solar system dynamics, the nature of matter passing between stars, and yes, the uncomfortable question of whether we're alone. Around the same time 3I-ATLAS began its anomalous acceleration, geophysicist Stephen Burns issued a stark warning. Earth, he claimed, is entering a big wave of energetic activity. Solar flares were intensifying. Geomagnetic storms were battering the planet's magnetic field. Seismic events were clustering in unusual patterns. Burns pointed to a convergence of factors: a 28-day recurrence cycle of coronal holes in the Sun, the peak of the Taurid meteor stream in early November, a supermoon event on November 5th, and upcoming planetary alignments. His argument suggested that these weren't isolated incidents but pieces of a larger pattern, an energetic crescendo building across multiple systems. The timing creates an intriguing coincidence. Here's an interstellar visitor doing something unexplained at the same moment our star and planet appear to be ramping up their activity. Coincidences happen, of course. The universe is vast and events overlap without connection all the time. But when you're dealing with anomalies, coincidences start to look like clues. They start to whisper that maybe, just maybe, there's a broader context we're missing. This video will take you through the evidence, the anomalies, and the hypotheses, natural and otherwise. We'll examine the data that makes scientists nervous. We'll explore what happens when you try to fit 3I-ATLAS into our existing models of cometary behaviour and watch those models strain under the pressure. We'll consider alternatives that sound like science fiction but might be science fact. We'll place this object in the context of other interstellar visitors, the roiling energy environment of our solar system, and the cutting-edge discoveries reshaping our understanding of small bodies and fundamental physics. And we'll ask the question that nobody wants to ask too loudly yet. What if this object isn't just a comet? What if it's signalling something far bigger? Time 0.5s. Part 2. Why the A3 equals 0 condition is fundamental. Let's talk about how comets are supposed to misbehave, because understanding normal will help you see why 3I-ATLAS is anything but. When a comet approaches the Sun, solar radiation heats its surface. Ice sublimates directly from solid to gas, skipping the liquid phase entirely. This creates jets of vapour that carry dust particles along for the ride. Those jets escape through vents or cracks in the nucleus, and depending on where those vents are located and how the nucleus is oriented at any given moment, the thrust vector points in different directions. The nucleus is almost certainly rotating, tumbling through space on some complex axis. As it spins, different vents face the Sun at different times. The result is a thrust vector that wanders through three-dimensional space, pushing the comet radially, tangentially, and out of the plane of its orbit. Most comets show significant out-of-plane acceleration. The A3 component is rarely zero because nature is chaotic. Surface features vary. Rotation states are complex. The timing of vent activation depends on thermal conductivity, subsurface structure, and volatile distribution, all of which differ from one patch of surface to another. You get thrust up, down, sideways, in combinations that change as the comet rotates and as solar heating varies with distance. The orbital modelers who track these objects routinely fit all three components, because that's what the data demands. Statistical surveys of cometary non-gravitational forces show this clearly. When you sample dozens or hundreds of comets, the distribution of A3 values spreads across a wide range. Some comets have small out-of-plane components, others have large ones, but perfect zero is vanishingly rare. You might get A3 close to zero if the observation arc is short or the acceleration is weak. But when you have sustained acceleration over weeks and a good observational baseline, 0 A3 becomes a statement. It says the thrust is confined, disciplined, aligned with a single plane. 3I-ATLAS returned A3 equals 0 within the measurement uncertainty of the JPL horizon's orbital fit. The residuals, the tiny differences between where the object was predicted to be and where it was actually observed, don't demand any out-of-plane component. The fit works without it. That's not an artifact of insufficient data. The observational coverage included multiple sites over an extended arc. The astrometric precision was high. If there had been meaningful out-of-plane thrust, the fit would have picked it up. So what does it mean when an object accelerates for 20 days without deviating from its orbital plane? It means the mechanism producing that thrust is either extremely stable or extremely controlled. For natural venting to achieve this, you'd need a configuration where jets fire only in directions that lie within the plane, never perpendicular to it. Imagine a nucleus shaped just right, oriented just so, with vents positioned such that their combined thrust cancels out any perpendicular component, while reinforcing radial and tangential ones. It's not impossible, but it requires a level of geometric precision that nature rarely provides. One hypothesis is uniform vent distribution. If the nucleus has many small vents spread evenly across its surface, and if those vents all vent at similar rates, the thrust vectors might average out to produce a net force within the plane. But this requires symmetry. It requires that the rotation axis aligns in a very specific way with the orbital plane. It requires that surface composition and thermal properties are uniform enough that no one hemisphere dominates the outgassing. Each of those requirements individually is a stretch. All of them together start to look contrived. Another hypothesis involves an unusual volatile composition. Maybe 3I-ATLAS is rich in something like carbon monoxide or nitrogen, volatiles that sublimate at high velocity but carry little dust. High-velocity gas jets produce more thrust per unit mass lost, which could explain the acceleration without a visible coma. But this still doesn't explain the planar confinement. Gas jets from a rotating body should still have out-of-plane components, unless the spin axis and vent geometry conspire in just the right way. A third option is micro-outgassing, tiny jets ejecting particles at high speed, but in quantities too small to resolve with current telescopes. This might explain the lack of visible coma, but again, it doesn't solve the A3 problem. Microjets should still vary in direction as the nucleus rotates, producing some out-of-plane thrust unless the system has remarkable symmetry. The 0A3 condition opens the door to more exotic interpretations. If you were designing a propulsion system for a small spacecraft, you'd want to keep your thrust vector aligned with your trajectory. You wouldn't waste propellant pushing perpendicular to your motion. You'd fire engines in the plane of your orbit to adjust speed and direction efficiently. A perfectly planar thrust profile is exactly what you'd expect from controlled propulsion. That doesn't mean 3I-ATLAS is a spacecraft. It means that the thrust signature we're seeing is more consistent with active control than with passive, chaotic outgassing. It's a puzzle piece that fits better in one picture than another, even if that picture makes us uncomfortable. Consider the alternative. If 3I-ATLAS is venting naturally, then we're witnessing a cosmic coincidence of geometry, composition, rotation state, and timing so precise that it mimics artificial behaviour. Nature can be surprising, but it rarely looks this tidy. If there's no visible venting or coma, then what is producing the thrust? Part 3. Absence of coma. Slash-tail, observational paradox. Telescopes around the world have been watching 3I-ATLAS. Ground-based observatories, space-based assets, professional and amateur astronomers all pointed their instruments at this interstellar visitor as it made its swing through the inner solar system. They measured its brightness, tracked its position, searched for any signs of activity. What they found was a remarkably quiet object. The magnitude of 3I-ATLAS remained stable, hovering around 14.7 to 14.9. For context, that's far too faint to see with the naked eye, but well within reach of moderate-sized telescopes. The brightness didn't show the typical variations you'd expect from a comet waking up near perihelion. There were no sudden brightenings, no outbursts, no gradual increase as sublimation rates climbed. The light curve looked more like an asteroid than an active comet. When a comet undergoes strong outgassing, you see consequences. A coma develops, a fuzzy cloud of gas and dust surrounding the nucleus. This coma can extend for thousands or even hundreds of thousands of kilometers, glowing as sunlight scatters off the particles and as molecules fluoresce under ultraviolet radiation. Depending on the geometry, you see a tail form, swept back by solar wind and radiation pressure. Jets might become visible, narrow streams of material erupting from specific vents on the nucleus. The object's appearance changes, its brightness varies, morphology becomes complex. 3I-ATLAS showed none of this. High-resolution imaging failed to resolve any significant coma. No large tail stretched behind the object. No jets were visible in the data released to the public. The object appeared point-like, more akin to a bare rock than a venting comet. Spectroscopic observations, if available, should have detected emission lines from volatile gases like water vapour, carbon monoxide, carbon dioxide, or cyanogen. These lines serve as fingerprints, revealing what's boiling off the surface, yet reports suggested minimal or absent gas signatures, as if the object wasn't venting at all. Now let's run some numbers. To produce a velocity change of 60 meters per second over 20 days, 3I-ATLAS had to be pushed by something. If that something is outgassing, we can estimate how much mass needs to be expelled and at what velocity. The rocket equation tells us that delta V equals exhaust velocity times the natural log of initial mass divided by final mass. For a small body with uncertain mass, this gets speculative quickly, but we can make order of magnitude estimates. Assume the nucleus has a mass of a few million kilograms, maybe 10 million for argument's sake. To get 60 meters per second of delta V with gas venting at a few hundred meters per second, typical for water vapor or carbon monoxide sublimation, you'd need to lose a significant fraction of your mass. Let's say a few percent. That translates to hundreds of thousands of kilograms of material, ejected into space. Where did it go? A few 100,000 kilograms of gas and dust should create a visible coma. Dust particles scatter sunlight efficiently. Even if the dust production rate is low, the accumulation over 20 days should build up a detectable envelope. The fact that observers aren't seeing this presents a problem. Maybe the dust-to-gas ratio is extremely low. Maybe 3I-ATLAS is venting pure gas with almost no dust entrained. Gas alone is harder to see unless you catch the spectral emission lines. But even pure gas plumes should show up in sensitive spectroscopy, and the early reports don't confirm strong gas emissions either. Maybe the venting is happening in such tiny quantities, spread over such a large surface area, that the gas disperses instantly and never builds up a dense coma. Microjets, invisible individually, sum to produce the thrust. This is possible, but it requires a very specific surface structure and venting regime. Most comets don't work this way. They concentrate activity into relatively few vents, producing discrete jets rather than a diffuse haze. Another angle, maybe the particles being ejected are extremely small, nanoparticles or even molecules, that don't scatter light efficiently in the visible wavelengths we're observing. Smaller particles scatter more in the ultraviolet and infrared. If 3I-ATLAS is venting material optimized for invisibility in optical wavelengths, it could be accelerating without looking like it's accelerating. But now we're invoking a very particular particle size distribution and composition, adding another layer of contrivance to the natural explanation. The paradox sharpens. Acceleration implies force. Force implies mass ejection if we're talking about rocket thrust. Mass ejection should produce observable signatures. Those signatures are missing. Either the ejection is happening in a way we don't fully understand, or the force isn't coming from mass ejection at all. If venting is absent or invisible, what else could produce the thrust? Part 3. Natural outgassing hypotheses under stress. Let's give natural explanations their due. Let's take each hypothesis seriously, walk through the physics, and see where it leads. Science works by testing ideas against evidence, and we owe it to ourselves to exhaust the mundane before embracing the extraordinary. Hypothesis 1. Uniform vent distribution. Picture the nucleus of 3I-ATLAS as a roughly spherical body covered in many small vents. As solar heating penetrates the surface, ice beneath each vent sublimates and escapes. If the vents are evenly distributed and all vent at similar rates, the thrust vectors from individual jets might combine into a net force that happens to lie within the orbital plane. The key word is happens. This requires that the rotation axis of the nucleus aligns, such that the distribution of active vents, averaged over time, produces no net, perpendicular component. For this to work, the nucleus must have a specific spin state. Its rotation axis needs to be perpendicular to the orbital plane, or close to it, so that as it spins, vents on all sides vent symmetrically. The surface composition must be uniform enough that no hemisphere dominates. Thermal conductivity must be consistent, so that heating patterns don't create localized hotspots with stronger venting. Each of these conditions is plausible in isolation. Together they form a narrow target. Most comets don't have such precise symmetry. Their surfaces are patchy, their shapes irregular, their spin axes tilted at arbitrary angles. Finding an object that meets all these requirements by chance is unlikely. Hypothesis 2. Unusual volatile composition. Maybe 3I-ATLAS is rich in highly volatile ices like carbon monoxide, carbon dioxide, or molecular nitrogen. These substances sublimate at lower temperatures and higher velocities than water ice. High velocity ejection means more thrust per kilogram of mass lost. If the dust content is low, you get acceleration without a prominent coma. Carbon monoxide sublimates efficiently even at large distances from the Sun, which could explain sustained acceleration over an extended arc. The physics checks out. Carbon monoxide has been detected in other comets, and it does create thrust. But this hypothesis still faces the E3 problem. Unless the volatile distribution and vent geometry are precisely aligned, you should get thrust in all 3 dimensions. You'd also expect to see spectral signatures of carbon monoxide in emission if it's driving the acceleration. Observers should detect it. If they're not, either the observations are missing it, or it's not there in the quantities required. Hypothesis 3. Micro-outgassing and mass shedding. Instead of large jets, imagine the surface releasing material gradually through countless tiny vents, or through direct sublimation across the entire sunlit hemisphere. The gas and dust production rate per unit area is low, but integrated over the entire surface and over weeks, it adds up to enough thrust to produce the observed acceleration. Because the ejection is diffuse, it doesn't create a concentrated coma, just a faint haze that current instruments can't resolve. This scenario requires extremely fine-grained activity. The surface must be porous enough to allow gas to percolate through and escape everywhere, not just at discrete vents. The thermal wave from solar heating must penetrate the subsurface efficiently, driving sublimation below the surface layer. The escaping gas must carry little dust, or dust so fine that it's invisible. It's a delicate balance. Too much dust, and you get a coma. Too little gas, and you don't get enough thrust. Getting it just right, and maintaining that balance for 20 days, demands a level of control that nature doesn't usually provide. All 3 hypotheses face a common challenge: the observational constraints. The lack of visible coma and tail isn't just a minor inconvenience for these models, it's a central tension. Every mechanism we invoke to explain the thrust predicts observable consequences, and those consequences are absent. We can add epicycles, invoke special conditions, fine-tune parameters, but at some point we have to ask whether we're contorting the explanation to fit the data or following where the data actually leads. Thermal modelling compounds the problem. A small body in the inner solar system receives intense solar heating on its day side. That energy drives sublimation. The rate of mass loss depends on the volatile content, the thermal conductivity, the rotation period, and the surface albedo. For 3I-ATLAS to maintain steady thrust over 20 days without visible outgassing, all these factors must align in a very specific way. The nucleus must be small enough to avoid having large gravity that makes ejection inefficient, but massive enough to contain sufficient volatiles to sustain thrust. It must rotate fast enough to spread heating around, but not so fast that centrifugal forces dominate. It must have surface properties that suppress dust entrainment but allow gas escape. Each added constraint narrows the parameter space. What started as a broad category of natural explanations, comets vent when heated, has become a needle we're trying to thread. None of these hypotheses are impossible. Nature surprises us, but they're under stress, and that stress matters. So if natural hypotheses strain, let's turn our gaze to the more exotic possibilities. Part 5. Artificial/exotic hypotheses. Light sail, propulsion, or unknown physics. Now we enter speculative territory, and we need to be clear about that from the start. What follows are ideas, not established facts. They're scenarios that fit some of the data, but lack definitive proof. Science demands extraordinary evidence for extraordinary claims, and we're not there yet. But given the anomaly we're facing, these ideas can't be dismissed without consideration. Hypothesis 1. A thin reflective sail driven by radiation pressure. Imagine a structure with extremely low mass and high surface area, essentially a mirror tumbling through space. Sunlight hits the surface and reflects, transferring momentum. The force is small, but applied continuously over days or weeks, it adds up. The key parameter is areal mass density. mass per unit area. For a sail to accelerate noticeably under solar radiation, it needs to be very thin, perhaps a few micrometers or less, with high reflectivity. Let's run the numbers. Solar radiation pressure at 1 astronomical unit from the Sun is about 4.5 micronewtons per square metre. If 3I-ATLAS has an effective area of, say, a few square kilometres and a total mass of a few thousand kilograms, the acceleration could reach the observed 10 to the negative 6th astronomical units per day squared. The specifics depend on reflectivity, orientation, and distance from the Sun, but the order of magnitude works. A sail would naturally produce thrust aligned with the sun line, primarily radial, but if the sail is tilted relative to the Sun, the thrust vector rotates. Depending on orientation and spin, you could get components both radial and tangential, fitting the A1 and A2 values. The A3 equals 0 condition is satisfied if the sail's spin axis or orientation keeps it within the orbital plane, which isn't implausible for a thin structure subject to torques from radiation pressure and maybe interstellar magnetic fields. The absence of a coma fits perfectly. A sail doesn't outgas, it reflects. It would look like a faint, steady point of light, exactly what observers report. The challenge is explaining how such a structure formed. Natural processes don't build sails. Ice flakes or thin dust sheets might mimic sails briefly, but maintaining coherence and orientation over weeks is hard to justify. If 3I-ATLAS is a sail, it's likely engineered. Hypothesis 2. Controlled propulsion. Suppose 3I-ATLAS contains a propulsion system, chemical, electric, nuclear, or something more exotic. The system fires periodically or continuously to adjust the object's trajectory. The thrust is directed intentionally, which explains the precise planar confinement. The absence of visible exhaust could mean the propellant is something we don't easily detect, or the exhaust velocity is so high that the plume disperses instantly. For a chemical rocket, you'd need propellant mass and an engine. To achieve 60 meters per second delta V with a typical exhaust velocity of a few kilometers per second, you'd expend a small fraction of the total mass. A small spacecraft could carry enough fuel. Electric propulsion, like ion drives, operates at much higher exhaust velocities, requiring even less propellant. The trade-off is power. You need an energy source, solar panels, a nuclear battery, something to run the engine. This raises the obvious question, why? If 3I-ATLAS is a spacecraft, what's its mission? Why thrust midway through the solar system? Maybe it's performing a course correction, aiming for a specific target. Maybe it's decelerating after an interstellar journey. Maybe the thrust is part of a data collection or communication protocol we don't understand. Or maybe it's malfunctioning, firing thrusters unintentionally. Without knowing intent, we're guessing. But the pattern of thrust looks purposeful, not random. Hypothesis 3. Unknown physics. What if the acceleration comes from a mechanism science hasn't characterized yet? Examples include dark matter drag, where 3I-ATLAS passes through a clump of dark matter particles that exert a subtle force, or electromagnetic interactions, where the object carries a charge and interacts with the solar wind's magnetic field in an unexpected way, or solar system boundary, effects, some property of the heliosphere or galactic cosmic ray wind that influences motion in ways we haven't modelled. These ideas live on the frontier. Dark matter is still poorly understood. We know it exists from gravitational effects on galaxies, but its properties and interactions remain mysterious. If dark matter can exert drag on ordinary matter under certain conditions, then objects passing through regions of higher dark matter density might experience forces. The magnitude required to explain 3I-ATLAS's acceleration is far beyond current dark matter models, but those models are incomplete. Electromagnetic scenarios require that 3I-ATLAS has a significant charge or magnetic moment. Interstellar space is filled with charged particles, protons, electrons, heavier ions. If an object is charged, those particles exert forces. The solar wind also carries a magnetic field. Interactions between moving charges and magnetic fields produce forces. Could this explain the thrust? The problem is scale. The solar wind pressure and magnetic forces on a small body are typically much weaker than the observed acceleration. You'd need extraordinary conditions or amplification mechanisms we don't know about. Comparing these exotic hypotheses to the data, the sail scenario fits best. It explains the planar thrust, the absence of coma, and the consistent brightness. Controlled propulsion fits almost as well, but introduces questions of motive and origin. Unknown physics is the wild card, conceptually possible, but lacking a fleshed-out mechanism. Each hypothesis requires further evidence. For a sail, we'd want measurements of albedo and reflectivity, searching for unusually high values. For propulsion, we'd look for directional changes, velocity adjustments that correspond to deliberate maneuvers. For unknown physics, we'd need theoretical breakthroughs and independent observations of similar effects elsewhere. The extraordinary nature of these claims can't be overstated. Saying 3I-ATLAS might be a sail or spacecraft is not a casual assertion. It's a hypothesis born from anomalies that resist conventional explanations. We're not claiming proof. We're saying the data makes us uncomfortable, and when data makes you uncomfortable, you explore all possibilities, even the ones that sound like science fiction. Now that we've seen the anomaly and the hypotheses, let's broaden the context. How does this fit into the larger tapestry of interstellar objects, solar system energy, and hidden angles? Part 6. Interstellar Objects and Comparative Behaviour. Interstellar objects are visitors from beyond. They formed around other stars, were ejected from their home systems by gravitational interactions, and wandered the galaxy for millions or billions of years before stumbling into ours. Until recently they were theoretical. We knew they had to exist. Probability alone guaranteed it, but we'd never seen one. Then, in October 2017, the Pan-STARRS telescope in Hawaii spotted something moving fast, too fast to be bound to the sun. Astronomers scrambled to observe it before it left. They named it 3I-ATLAS, Hawaiian for scout or first distant messenger. Oumuamua was strange. Its trajectory was hyperbolic, confirming its interstellar origin. Its shape appeared highly elongated, possibly 10 times longer than wide, like a cigar or pancake tumbling end over end. Its light curve showed periodic brightness variations consistent with that elongation. And as it receded from the sun, it showed non-gravitational acceleration, a small but significant push that couldn't be explained by gravity alone. Some proposed outgassing, even though no coma or tail was visible. Others suggested more exotic ideas, including the possibility that it was a light sail, either natural or artificial. The debate around Oumuamua grew heated. Most scientists favoured natural explanations, arguing that unusual outgassing or asymmetric shape could produce the observed acceleration without visible coma. A minority, including Harvard astronomer Avi Loeb, argued that the data was more consistent with a thin, reflective object driven by radiation pressure, potentially an artifact. The controversy highlighted how little we know about interstellar objects, and how quickly assumptions can be challenged when data doesn't fit expectations. In August 2019, a second interstellar visitor arrived. 2 was Borisov. Unlike Oumuamua, Borisov looked like a comet, plain and simple. It developed a prominent coma and tail as it approached the sun. Spectroscopy revealed familiar volatiles, water, carbon monoxide, cyanogen. Its behaviour matched what astronomers expect from comets, just one that originated outside our solar system. Borisov reassured the community that most interstellar objects are probably ordinary, that Oumuamua might be the exception rather than the rule. Now we have 3I-ATLAS, and it's neither Oumuamua nor Borisov. It shares traits with both, but fits neither mould. Like Oumuamua, it shows non-gravitational acceleration without visible outgassing, raising questions about what's driving the thrust. Like Borisov, it follows a trajectory that could be cometary, entering the inner solar system and experiencing solar heating. But its thrust profile, that precise planar confinement, sets it apart. Oumuamua's acceleration had radial and tangential components, but also uncertainties that might have hidden out of plane effects. Borisov's outgassing was clearly three-dimensional, typical of an active comet. 3I-ATLAS is threading a middle path, anomalous but in a different way. This raises the question, is 3I-ATLAS simply another interstellar visitor behaving oddly, or is it a fundamentally different kind of object? If we're seeing 3 distinct interstellar objects in less than a decade, each with unique characteristics, what does that tell us? About the population? Extrapolating from this tiny sample is dangerous. We don't know the selection biases. Brighter objects are easier to find. Highly reflective or unusually active objects might be overrepresented. We're fishing with a small net in an ocean of possibilities. Consider detection bias. Current surveys find interstellar objects when they're relatively close and bright. Fainter, smaller or less active objects slip through unnoticed. If there's a population of low-mass, sail-like structures drifting between stars, we might only detect them when they're near perihelion and sunlight makes them visible. The same applies to small inert bodies that only show up as faint points of light. The population of interstellar objects could be vastly more diverse than our 3 data points suggest. Imagine a scenario where 3I-ATLAS is part of a fleet, a swarm of sails or probes launched by some civilization long ago, sent out to explore the galaxy. Most would pass through solar systems unnoticed, but occasionally one gets spotted because it brightens as it nears a star. This is speculative, bordering on wild, but it's not ruled out by the data. If intelligent civilizations exist and have mastered interstellar travel or communication, sending lightweight probes is a plausible strategy. Thin sails, accelerated by starlight, carrying minimal payloads, could traverse enormous distances over millennia. Or maybe 3I-ATLAS is a fragment, a piece of an engineered structure that broke apart eons ago. Maybe it's a discarded component, space junk from an alien system drifting on galactic currents. Or maybe it's entirely natural, a type of object we haven't characterized yet because we've never had the chance to study interstellar material up close. Maybe comets from other stellar systems form in environments different from ours, with compositions or structures that produce unusual venting regimes. Comparing behaviour across interstellar objects frames whether 3I-ATLAS is an outlier or a tipping point. If every interstellar object we find shows anomalies, then anomalies become the norm, and we adjust our expectations. If 3I-ATLAS stands alone, it becomes the puzzle demanding explanation. Right now, with only 3 examples, we can't say. But the pattern is suggestive. Interstellar objects don't behave like solar system natives. They surprise us. They challenge assumptions, and each new discovery expands the envelope of what we consider possible. Having looked outward to other interstellar objects, let's turn inward to our own solar system's energy environment and how it might influence such behaviour. Part 7. The Solar System Energy Environment. Solar flares, CMEs, and geomagnetic activity. The Sun is not a constant, placid ball of light. It's a roiling nuclear furnace wrapped in a magnetic dynamo, and its moods change on timescales from minutes to decades. Right now, in late 2025, the Sun is ramping up. Solar cycle 25, which began in late 2019, is approaching its maximum phase, the period of peak activity when sunspots multiply, solar flares erupt, and coronal mass ejections blast plasma into space. Solar flares are sudden releases of magnetic energy stored in the Sun's atmosphere. They appear as brilliant flashes in extreme ultraviolet and X-ray wavelengths, releasing as much energy as millions of hydrogen bombs. Flares are classified by their X-ray intensity. A class, B class, C class, M class and X class, each step representing a 10-fold increase in power. M class flares are medium strength, capable of causing brief radio blackouts on Earth's dayside. X class flares are the giants, able to trigger radiation storms and disrupt satellite electronics. Coronal mass ejections, or CMEs, are even more dramatic. These are massive eruptions of plasma and magnetic field from the Sun's corona, hurled into interplanetary space at speeds of hundreds to thousands of kilometers per second. When a CME slams into Earth's magnetosphere, it compresses the magnetic field, inducing electric currents in the ionosphere and on the ground. Geomagnetic storms follow, causing auroras at high latitudes, disrupting power grids, degrading GPS signals, and exposing astronauts to radiation. In 2025, observers have recorded multiple M-class and X-class flares, along with several significant CMEs. The frequency of these events is rising as the solar cycle progresses toward maximum, expected around 2025 or 2026. High-speed solar wind streams flowing from coronal holes have battered Earth's magnetosphere, producing recurring geomagnetic disturbances on a roughly 27-day cycle, the rotation period of the Sun as seen from Earth. So what does this have to do with 3I-ATLAS? Small bodies in the solar system aren't immune to the Sun's fury. Solar radiation and solar wind affect them in multiple ways. Radiation pressure pushes on their surfaces, a force we already discussed in the context of light sails. Charged particles in the solar wind can sputter atoms off exposed surfaces, eroding material molecule by molecule. Photoelectron emission, where ultraviolet light knocks electrons off the surface, can charge the object, creating electric fields that interact with the solar wind's magnetic field. For icy bodies, solar heating drives sublimation, the primary mechanism behind comet activity. But enhanced solar output during flares or CMEs could temporarily increase heating rates, triggering bursts of venting. Alternatively, if the object is charged, interactions with the solar wind plasma might exert forces, adding to or modifying the thrust from radiation pressure or venting. These mechanisms are subtle, typically producing effects far smaller than the observed acceleration of 3I-ATLAS, but in principle, they could contribute. The temporal coincidence is intriguing. 3I-ATLAS's anomalous acceleration was detected in November 2025, during a period of elevated solar activity. Stephan Burns pointed to this same time frame, noting a convergence of factors: the 28-day recurrence of coronal holes, peak Taurid meteor activity, a supermoon, and what he called a big wave of energetic disturbances affecting Earth. Is this connection real or coincidental? Let's quantify the forces. Solar wind pressure at 1 astronomical unit is roughly 1 to 6 nanopascals, depending on whether you're in slow or fast wind. For an object with a cross-sectional area of a square kilometre, that translates to forces on the order of millinewtons. Compare that to the force needed to produce 3I-ATLAS's acceleration. If the object has a mass of millions of kilograms, you need forces on the order of newtons to tens of newtons, thousands of times stronger than solar wind pressure alone. Solar wind can't be the primary driver. Radiation pressure is stronger, about 4.5 micropascals at 1 astronomical unit, but even that falls short unless the object has extraordinary properties, like the low aerial mass of a sail. Enhanced solar output during flares might increase radiation pressure by a few percent temporarily, nowhere near enough to explain continuous acceleration over 20 days. What about electromagnetic interactions? If 3I-ATLAS carries a significant electric charge, perhaps accumulated through photoelectron emission or interaction with interstellar plasma before entering the solar system, it could interact with the sun's magnetic field embedded in the solar wind. A moving charge in a magnetic field experiences the Lorentz force, perpendicular to both velocity and field. Depending on the charge and field strength, this could produce forces, but again, the magnitudes are small. The solar wind magnetic field at 1 astronomical unit is about 5 nanoteslas. To get substantial force, you'd need enormous charges, far beyond what photoemission or typical charging mechanisms can provide. Perhaps there are unknown couplings, amplification mechanisms where solar activity triggers responses in the object's surface or interior that we haven't modelled. For instance, if 3I-ATLAS has a highly conductive surface, rapidly changing magnetic fields from CMEs could induce eddy currents, creating magnetic moments that interact with the solar wind. This is wildly speculative and would require exotic material properties, but it's conceptually possible. The more plausible link is indirect. Solar activity affects the entire heliosphere, the bubble of solar wind and magnetic field that surrounds the solar system. Changes in solar output alter the density, temperature, and magnetic structure of this environment. Small bodies passing through might experience different conditions than they would during solar minimum. If 3I-ATLAS is venting, enhanced solar heating or altered ambient pressure could modulate the venting rate or direction. If it's a sail, variations in radiation pressure or magnetic torques could change its orientation, affecting thrust. The challenge is that none of these mechanisms neatly explain the observations. The acceleration is sustained and planar, not sporadic or responsive to solar flares. There's no obvious correlation between flare events and changes in 3I-ATLAS's trajectory. The connection remains speculative, a tantalizing coincidence rather than a demonstrated cause, but coincidences accumulate. Burns warned of a big wave, and 3I-ATLAS started behaving strangely. The sun is more active, and an interstellar visitor is doing something unexplained. Maybe these events are independent, maybe they're not. The universe is interconnected in ways we're still learning. Forces and fields permeate space, linking distant objects through subtle interactions. When multiple systems show anomalies simultaneously, it's worth asking whether they share a root cause. If our sun and heliosphere might be playing a role, could Earth itself also be part of a bigger energetic picture? That leads into seismic and big wave narratives. Part 8. Seismic activity, Earth effects, and the big wave narrative. Stefan Burns is not a household name, but among those who track geophysical phenomena and space weather, his warnings carry weight. In late 2025, Burns issued a stark alert. Earth is entering a period of intensified energetic activity, a convergence he termed the big wave. His argument rests on multiple factors aligning in time, each potentially influencing geological and atmospheric systems. First, the 28-day recurrence cycle of coronal holes. Coronal holes are regions in the Sun's atmosphere where the magnetic field opens into space, allowing high-speed solar wind to escape. These holes persist for weeks or months, and as the Sun rotates every 27 days, the same hole can face Earth repeatedly, sending pulses of fast wind toward us. Each pulse compresses the magnetosphere, inducing geomagnetic storms. Burns noted that in late 2025, a particularly active coronal hole was producing strong recurring disturbances, hammering Earth's magnetic field every 4 weeks. Second, the torrid meteor stream. Earth passes through the torrid stream twice a year, once in late October and early November, and again in late June and early July. The stream contains debris from Comet Encke, and possibly fragments of larger bodies that broke apart millennia ago. In early November 2025, Earth traversed the densest part of the stream, encountering more meteors and potentially larger particles than usual. Some researchers have speculated that meteor impacts, even small ones, could trigger atmospheric or seismic effects, though evidence is scant. Third, the supermoon on November 5, 2025. A supermoon occurs when the full moon coincides with the moon's closest approach to Earth in its elliptical orbit. The moon's gravitational pull on Earth is slightly stronger during these events, increasing tidal forces. Tides affect not just oceans but also the solid Earth, causing measurable crustal deformation. Some studies suggest that tidal stresses might influence earthquake timing, particularly for faults already near failure. Fourth, planetary alignments. Burns mentioned upcoming alignments of Jupiter, Saturn, and other planets, configurations that allegedly concentrate gravitational influences on the Sun and Earth. Astrologers have long claimed such alignments matter, but mainstream science is skeptical. The gravitational forces from distant planets on Earth are minuscule compared to the Moon's and Sun's tidal forces. Any effect would be lost in the noise. Burns tied these factors together, arguing that their simultaneous occurrence creates a window of heightened energetic activity, manifesting as increased solar flares, geomagnetic storms, and importantly, seismic events. He pointed to recent earthquakes, a magnitude 6+ event in Kamchatka, Russia, another in Afghanistan, and tremors elsewhere, as evidence that Earth's crust is responding to this convergence. The scientific community's response to such claims is mixed at best. The idea that solar or geomagnetic activity triggers earthquakes has been studied for decades with inconclusive results. Some research finds weak correlations between geomagnetic storms and shallow seismicity, particularly in volcanic regions where magma movement might be influenced by electrical currents or pressure changes. Other studies find no correlation, attributing apparent patterns to statistical noise or publication bias. The consensus is that while external forces like tides can modulate earthquake timing slightly, they don't cause earthquakes. Tectonic stress builds up over years or centuries, and external triggers at best nudge already primed faults over the edge. The problem with the big wave narrative is distinguishing signal from noise. Earthquakes happen constantly. Magnitude 6 events occur hundreds of times per year globally. Solar flares and geomagnetic storms are common during solar maximum. Supermoons happen every year or two. Meteor showers are predictable. When you look for patterns in noisy data, you often find them, even if they're coincidental. Humans are pattern-seeking creatures, and our brains excel at seeing connections that may not exist. That said, dismissing Burns outright would be premature. Science progresses by examining anomalies and testing hypotheses. If there's a real physical mechanism linking solar activity to seismicity, uncovering it requires serious investigation, not reflexive skepticism. Some researchers are exploring how geomagnetic disturbances might affect crustal conductivity, piezoelectric effects in rocks, or fluid pressure in fault zones. These are subtle effects hard to measure and harder to prove, but they're not impossible. Now, How does this connect to 3I-ATLAS? Burns didn't explicitly link his big wave to the interstellar object, but the timing invites speculation. If Earth is experiencing an energetic convergence, could the same processes affect objects passing through the solar system? Could enhanced solar wind or heliospheric disturbances influence 3I-ATLAS's behaviour? One angle is that both phenomena might share a common driver. Perhaps the solar system is passing through a region of interstellar space with higher density of charged particles or dust, affecting both Earth's magnetosphere and small bodies like 3I-ATLAS. The solar system moves through the galaxy at about 250 kilometers per second, and the local interstellar medium is not uniform. We pass through clouds of gas and dust, regions with varying density and temperature. If we've recently entered a denser region that could amplify solar wind interactions, increase meteor influx, and possibly exert forces on small bodies. Another angle is electromagnetic. Earth's magnetosphere and 3I-ATLAS, if charged, both interact with the heliospheric magnetic field. Changes in the sun's output alter that field structure. Maybe the same magnetic fluctuations that trigger geomagnetic storms on Earth also affect 3I-ATLAS, inducing torques or forces that modify its trajectory. This is highly speculative and would require mechanisms we don't currently understand. A third angle is purely observational. Maybe the big wave is a cognitive frame, a narrative that groups unrelated events because they happen to coincide. 3I-ATLAS's anomaly, Earth's seismic activity, and solar storms might be independent, and connecting them is an example of apophenia, seeing meaningful patterns in random data. Science demands we test this possibility rigorously. Burns's claims are not mainstream, and many of his specific predictions or causal links lack strong evidence. But the temporal clustering he highlights is real. Multiple systems are showing activity in the same time frame. Whether that's coincidence, common cause, or interconnected processes remains an open question. The big wave narrative challenges us to think holistically about the solar system as a system, not a collection of isolated phenomena. Beyond solar and seismic narratives, there are hidden data controversies and social dynamics in the research community. Let's dig in. Part 9. Hidden angles and controversies in the community. Science is supposed to be objective, driven by data and logic, free from bias and politics. In practice, it's messier. Scientists are human. They have egos, careers, funding pressures, and social dynamics that shape what gets studied, what gets published, and what gets believed. The story of 3I-ATLAS plays out not just in telescopes and equations, but in conference rooms, peer review panels, and online forums where ideas clash and reputations are won or lost. Start with data transparency. The non-gravitational parameters for 3I-ATLAS, the A1, A2, A3 values, come from NASA's Jet Propulsion Laboratory Horizons system. Horizons is a public tool. Anyone can query it for orbital elements and predictions. But the underlying data, the astrometric observations that feed into the orbit fit, come from multiple sources. Professional observatories, amateur astronomers, sky surveys. Not all of that data is publicly available immediately. Some observations are proprietary, held by survey teams until they publish. Others are shared through the Minor Planet Center, a clearinghouse for asteroid and comet data, but with variable quality and completeness. Independent researchers have taken the available data and run their own orbit fits, posting results on forums, preprint servers, and social media. Some of these fits agree with JPL's solution, others diverge slightly, showing sensitivity to which observations are included and how residuals are weighted. Orbital mechanics is precise, but it's not immune to interpretation. Choosing which data points to trust, how to handle outliers, and what model to use for non-gravitational forces all involve judgment calls. Different analysts make different calls, and the results can shift. This creates a challenge. When someone claims 3I-ATLAS has 0 out-of-plane acceleration, are they reporting a robust finding, or an artifact of their particular dataset and fitting procedure? Peer review is supposed to catch such issues, but much of the discussion around 3I-ATLAS is happening outside formal channels. It's on Twitter, YouTube, Reddit, blogs. Ideas spread fast, peer review moves slow, and by the time official papers are published, the narrative may already be set. There's also the question of colour and reflectivity anomalies. Some observers have reported that 3I-ATLAS appears bluer than typical comets or asteroids, with a spectrum that suggests high reflectivity or unusual surface composition. Blue spectra can indicate fresh ice, lack of dust, or specific minerals. In the context of the light sail hypothesis, a very high albedo and blue colour would support the idea of a reflective surface. But measuring colour accurately is hard. It depends on phase angle, the angle between the sun, the object, and the observer. As phase angle changes, the brightness and colour of reflected light shift. Observers must correct for this, and the corrections rely on models that may not apply to unusual objects. Instrument calibration matters too. Different telescopes, different detectors, different filters all introduce systematic errors. Sky background, atmospheric absorption, and contamination from nearby stars add noise. When someone posts that 3I-ATLAS is anomalously blue, it's worth asking compared to what? Using which instruments? Corrected how? If the claim rests on a few data points, from a single observer, it's suggestive but not definitive. If multiple independent teams with different instruments confirm it, the claim strengthens. So far, the public evidence is sparse, and the scientific community is cautious. Speculative hypotheses face an uphill battle in academia. Proposing that 3I-ATLAS might be an artificial object or sail invites skepticism, sometimes outright dismissal. The peer review system is conservative by design, favouring explanations that fit within established frameworks. Papers that invoke new physics or extraordinary claims require extraordinary evidence, and reviewers hold them to higher standards. This is appropriate. Science should be rigorous, but it can also stifle innovation. If every unconventional idea is rejected before the evidence is fully gathered, we risk missing real discoveries. There's also a social dimension. Researchers who advocate for exotic explanations risk their reputations. Mainstream scientists may distance themselves, fearing association with fringe ideas. Funding agencies prefer safe bets, projects that promise incremental advances rather than paradigm shifts. Career advancement, tenure, and grant success depend on publishing in respected journals, and those journals favour conventional work. The result is a bias toward natural explanations, even when the data strains to fit them. Conversely, contrarian researchers who embrace speculative ideas can become isolated, forming their own communities where unconventional thinking is celebrated, but critical scrutiny may lapse. Echo chambers form where everyone agrees and dissenting voices are dismissed. This happens on both sides, the mainstream dismissing the fringe and the fringe dismissing the mainstream. Social media amplifies these dynamics. A single claim about 3I-ATLAS, backed by preliminary data, can go viral before it's vetted. YouTube channels, blogs, and podcasts seize on anomalies, spinning narratives that attract viewers but may not reflect scientific consensus. Mainstream scientists respond, sometimes dismissively, creating a perceived divide between official science and independent researchers. The public watches this unfold, unsure whom to trust. To what extent might community bias or publication bias influence how we interpret 3I-ATLAS's anomaly? It's impossible to quantify, but the effects are real. If researchers unconsciously favour natural explanations because those are easier to publish, they might not pursue exotic hypotheses with the same vigour. If contrarians overweight anomalies because those fit their worldview, they might ignore mundane explanations that actually work. Ideally, science self-corrects through replication, debate, and accumulation of evidence. But the process is slow and imperfect. The key is intellectual humility. Admitting we don't know is harder than it sounds. Scientists are trained to provide answers, and uncertainty feels like failure. But 3I-ATLAS is genuinely puzzling. The data doesn't fit neatly into existing boxes. Acknowledging the uncertainty, exploring multiple hypotheses without premature commitment, and waiting for better data is the most honest approach. Now that we've looked at context and controversy, we'll map the field of hypotheses and gauge which hold more promise and which are likely dead ends. Part 10. Hypothesis Matrix. Mapping possibilities and probabilities. Let's lay out the playing field. We have multiple competing hypotheses to explain 3I-ATLAS's behaviour, and each makes different predictions, requires different conditions, and matches the evidence to different degrees. The goal isn't to declare a winner yet, it's to map the space of possibilities and identify what observations would most decisively shift our confidence. Hypothesis: natural comet outgassing with uniform vents. Required conditions include a nucleus with many small, evenly distributed vents, a spin axis perpendicular to the orbital plane, so venting averages symmetrically, uniform surface composition and thermal properties, and sufficient volatile content to sustain thrust over 20 days. Current evidence that supports this includes the hyperbolic trajectory, suggesting interstellar origin, and objects with ice naturally vent. Evidence against includes the absence of visible coma or tail, stable brightness inconsistent with strong outgassing, and zero out-of-plane acceleration requiring extraordinary geometric precision. Key unknowns are nucleus size, shape, spin state, surface composition, and volatile distribution. Plausibility rating: moderate but strained. This is the default assumption for comets, but the lack of visible activity and precise planar thrust are difficult to reconcile. Hypothesis: unusual volatile composition, carbon monoxide or nitrogen rich. Required conditions include high abundance of supervolatiles that sublimate at low temperatures and high velocities, low dust to gas ratio minimizing visible coma, and vent geometry somehow confining thrust to orbital plane. Supporting evidence includes the possibility that interstellar objects formed in different environments with exotic compositions and supervolatiles can produce high thrust per unit mass. Evidence against includes the expectation of spectroscopic detection of carbon monoxide or carbon dioxide emissions, which have not been clearly reported, and the continued problem of planar thrust confinement. Key unknowns are detailed spectroscopy results and nucleus composition. Plausibility rating: moderate but faces observational gaps. Supervolatiles are plausible, but the lack of gas detections is troubling. Hypothesis: radiation pressure acting on a thin, low-mass sail-like structure. Required conditions include extremely low aerial mass, perhaps a few grams per square meter, high reflectivity approaching unity, orientation tilted to the sun producing both radial and tangential, thrust components, and structural coherence maintained over weeks. Supporting evidence includes perfect match to absence of coma or tail, since sails don't outgas, planar thrust natural for a thin structure confined by torques, consistent brightness if reflectivity is stable, and radiation pressure forces scaling appropriately at observed solar distances. Evidence against includes the requirement of artificial or extremely rare natural formation, and lack of direct measurement of high albedo or reflectivity yet. Key unknowns are albedo and reflectivity measurements, phase curve analysis, and structural imaging. Plausibility rating: low to moderate but compelling fit. If 3I-ATLAS has sail-like properties, this hypothesis becomes very strong. The barrier is proving such properties exist. Hypothesis: controlled propulsion from an engineered spacecraft. Required conditions include onboard propulsion system with propellant or energy source. Deliberate thrust applied for course correction or deceleration, minimal visible exhaust or exhaust too faint to detect, and purposeful behavior implying intelligence or programming. Supporting evidence includes precise planar thrust consistent with controlled burns, sustained acceleration over 20 days matching what an efficient propulsion system could deliver, and absence of coma fitting non-chemical propulsion like electric drives. Evidence against includes the extraordinary nature of the claim requiring extraordinary proof, unclear motive for thrusting mid-trajectory, and no other indicators of artificiality like radio emissions or structured geometry. Key unknowns are detection of any signals or emissions, trajectory changes indicating maneuvers, and higher resolution imaging. Plausibility rating: very speculative but cannot be ruled out. This is the most extraordinary hypothesis and demands the most rigorous evidence. Hypothesis: exotic physics such as dark matter drag or electromagnetic interactions. Required conditions include passage through a region of enhanced dark matter, density or charged particle concentration, novel coupling between object and interstellar or heliospheric medium, and effects producing forces on the order of 10 to the -6th astronomical units per day squared sustained over weeks. Supporting evidence includes theoretical possibility if new physics exists, and unexplained acceleration inviting new mechanisms. Evidence against includes lack of theoretical framework, predicting such effects at observed magnitudes, no independent evidence of anomalous dark matter or fields in this region, and forces from known exotic mechanisms far too weak. Key unknowns are measurements of local space environment and theoretical developments in dark matter physics. Plausibility rating, very low but conceptually open. This is the frontier wildcard, unlikely but not impossible. For each hypothesis, there are killer observations that would decisively shift probabilities, detection of a coma, or jets would strongly favour natural outgassing. Measurement of very high albedo approaching 100% would favour the sail hypothesis. Observation of trajectory changes corresponding to deliberate manoeuvres would favour propulsion. Detection of unusual emissions or spectral features might support exotic physics or reveal composition. High-resolution imaging showing structured geometry would hint at artificiality. The matrix reveals where our uncertainties lie. We desperately need better data, spectroscopy to detect or rule out gas emissions, photometry across multiple wavelengths to constrain albedo and reflectivity, astrometry over a longer arc to refine non-gravitational parameters, and if possible radar or resolved imaging to see the nucleus itself. Each measurement narrows the hypothesis space. Right now, we're in a state of productive confusion. Multiple hypotheses remain viable, and none can be ruled out with certainty. That's uncomfortable but honest. Science thrives in this space, where data challenges assumptions and forces us to think harder. The next 12 months will be critical, as more observations come in and as theorists refine models. In our final act, we'll zoom out further, looking at adjacent science stories from 2025 that may inform our thinking and expand the frame. Part 11. Recent breakthrough in AI and astrophysical surveying, 2025. Astronomy is drowning in data, and that's a good problem to have. The next generation of sky surveys, particularly the Vera C. Rubin Observatory's Legacy Survey of Space and Time, abbreviated LSST, promises to image the entire visible sky every few nights, generating tens of terabytes of data daily. Traditional analysis methods, where humans inspect images or run predefined algorithms, can't keep pace. Enter artificial intelligence. In 2025, multiple research groups announced breakthroughs in AI-driven anomaly detection for astronomical surveys. Machine learning algorithms, particularly deep neural networks, have been trained on vast datasets of known objects: stars, galaxies, asteroids, comets. Once trained, these networks can sift through new observations, flagging anything that doesn't fit established patterns. An object moving in an unexpected way, exhibiting unusual brightness variations, or showing spectral features that don't match known classes gets marked for follow-up. One notable example came from a collaboration using LSST precursor data. Their algorithm identified several faint-moving objects that had been missed by traditional detection pipelines. Some turned out to be distant trans-Neptunian objects, icy bodies beyond Neptune's orbit. Others were near-Earth asteroids on unusual trajectories, and one, intriguingly, showed signs of non-gravitational acceleration similar to what we see in 3I-ATLAS. The AI flagged it because its motion deviated from a purely gravitational path, and subsequent analysis confirmed thrust components that didn't match typical cometary outgassing. These techniques work by learning what normal looks like, then identifying outliers. For moving objects, normal means following Keplerian orbits, paths dictated by gravity. Deviations signal either measurement errors or real physical effects like venting, collisions, or, in exotic scenarios, propulsion. The algorithms can spot these deviations in data too noisy or subtle for human analysts to catch. Applied to 3I-ATLAS, AI tools might help detect faint coma or tail features invisible to standard processing. Machine learning can enhance images, pulling signal from noise by recognizing patterns in how light scatters or how faint structures appear. If there's a whisper-thin coma around 3I-ATLAS, an AI trained on images of active comets might see it where humans don't. AI also improves astrometry, the measurement of object positions. By analysing thousands of reference stars and accounting for systematic errors in telescope pointing, atmospheric distortion, and detector artifacts, algorithms can refine positions to sub-pixel accuracy. Better astrometry means tighter constraints on orbits and non-gravitational parameters. The A1, A2 are three values for 3I-ATLAS, could be refined with improved measurements, potentially revealing whether A3 is truly zero or just very small. Beyond detection and measurement, AI is being used for classification. Given an object's spectrum, light curve or orbit, algorithms can predict what type of object it is: asteroid, comet, trans-Neptunian object, interstellar visitor. These classifications rely on patterns learned from thousands of examples. When an object doesn't fit any class, it gets flagged as anomalous. 3I-ATLAS would likely trip such a classifier because it combines features of multiple classes: interstellar origin like Oumuamua, potential venting like comets, but planar thrust and no coma unlike either. The implications are significant. As survey sensitivity improves, the population of detected anomalies will grow. We might find dozens of objects behaving oddly, forcing us to expand our taxonomy. If several show sail-like properties, the sail hypothesis for 3I-ATLAS becomes less extraordinary. If many show planar thrust, we'd need to understand what natural mechanism produces that pattern. Conversely, if 3I-ATLAS remains unique, its oddity deepens. There's also the question of false positives. AI algorithms can be fooled, misidentifying noise as signal or overfitting to training data. Anomalies flagged by AI need human verification, spectroscopic follow-up, multi-wavelength observations. The pipeline from detection to confirmation involves multiple steps, each with potential for error, but the sheer volume of data makes AI indispensable. We can't afford to have humans review every image. We need smart filters that bring the interesting cases to our attention. Speculation. What if AI uncovers dozens of sail-like or anomalous movers in archival data, objects that passed through unnoticed years ago? That would suggest a population of such objects, changing how we interpret 3I-ATLAS. Instead of a lone weird visitor, it might be part of a class, natural or otherwise. The existence of a class implies a formation or deployment mechanism, something producing these objects in numbers. Alternatively, if AI surveys the sky for years and finds nothing else like 3I-ATLAS, that's also informative. It says such objects are rare, whether because they're naturally uncommon or because they're artifacts from a sparse population of probes. Rarity doesn't prove artificiality, but it adds to the mystery. The challenge moving forward is managing expectations. More data means more anomalies, but also more noise and misinterpretation. The interplay between human intuition and machine pattern recognition will define the next era of astronomy. 3I-ATLAS sits at the intersection of these trends, a puzzle that demands both cutting-edge tools and careful human judgment to solve. How might improved detection and analysis shift our understanding of 3I-ATLAS in the next 1 to 2 years? We'll likely have better orbit solutions, more refined non-gravitational parameters, deeper images searching for faint features, and comparisons to newly discovered similar objects. Each piece brings us closer to an answer. Part 12. Advances in Solar Physics, Major CME/Flare Event. This year, 2025. On March 19th, 2025, the Sun unleashed fury. An X3.7 class flare erupted from active region 3962, a sprawling cluster of sunspots near the Sun's equator. The flare peaked at 14:23 Coordinated Universal Time, flooding Earth's dayside with X-rays and extreme ultraviolet radiation. Radio operators reported widespread blackouts on high-frequency bands as the ionosphere absorbed the sudden surge of energy. But the flare was only the opening act. 30 minutes later, coronagraph images from the Solar and Heliospheric Observatory, or SOHO, revealed a massive coronal mass ejection blasting outward from the flare site. The CME carried billions of tons of magnetized plasma, expanding into a cloud hundreds of times larger than Earth. Its initial speed was clocked at over 2,000 kilometers per second, fast enough to reach Earth in less than 20 hours. When the CME struck Earth's magnetosphere on March 20th at 1100 UT, the impact was dramatic. The solar wind pressure spiked, compressing the magnetosphere and triggering a severe G4 geomagnetic storm. Auroras danced across skies as far south as the Mediterranean and northern United States. Power grid operators reported induced currents stressing transformers. Satellite operators maneuvered spacecraft to avoid the worst of the radiation, and astronauts aboard the International Space Station retreated to shielded modules. This event wasn't unique. It was one of several major flares and CMEs in 2025, but it exemplified the Sun's power during solar maximum. These events provide a natural laboratory for studying how solar output affects the space environment and objects within it. CMEs and flares change conditions throughout the heliosphere. Particle fluxes increase, bombarding planets, moons, and small bodies with protons, electrons, and heavier ions. These particles carry energy, eroding surfaces, sputtering atoms into space, and charging exposed materials. For icy bodies like comets, enhanced particle bombardment can alter sublimation rates or create electric fields on the surface. Radiation pressure fluctuates too. While the sun's luminosity in visible light changes by less than 0.1% during flares, ultraviolet and X-ray output can increase by orders of magnitude. Objects with high albedo in UV wavelengths experience stronger radiation pressure during flares, potentially producing temporary thrust variations. The solar wind's magnetic field, normally a few nanoteslas at 1 astronomical unit, can jump tenfold during CME passages. Rapidly changing magnetic fields induce electric currents in conductive materials. If 3I-ATLAS has metallic components or conductive ice, these currents could generate magnetic fields that interact with the solar wind, producing forces or torques. Could the March 19th event, or others like it, have triggered or amplified 3I-ATLAS's anomalous acceleration? The timing doesn't align perfectly. 3I-ATLAS's non-gravitational acceleration was detected in November, months after the March event, but solar activity remained elevated throughout 2025, with multiple M and X class flares and recurring CMEs. If there's a connection, it would need to be through sustained environmental changes rather than a single event. One possibility is cumulative effects. Repeated CMEs and high-speed streams erode surfaces over time. If 3I-ATLAS entered the inner solar system during a period of high activity, its surface might have been modified, exposing fresh volatiles or altering its reflective properties. This could change how it responds to solar heating or radiation pressure. Another angle is plasma interactions. The solar wind is a plasma, a gas of charged particles. Objects moving through plasma can develop bow shocks, regions where the plasma flow is disturbed. If 3I-ATLAS is charged, its interaction with the plasma could be complex, potentially generating forces. During CME passages, the plasma density and velocity spike, intensifying these interactions. But again, the forces involved are typically small, much weaker than the observed acceleration. Theoretical work in 2025 has explored how extreme solar events affect small bodies. One study modelled dust ejection from asteroids during CME impacts, finding that electrostatic forces can levitate dust particles off the surface, creating transient clouds. If 3I-ATLAS is shedding dust electrostatically rather than through sublimation, it might explain the lack of visible coma. The dust disperses too quickly to form a concentrated cloud, but this mechanism produces intermittent, not sustained, thrust. The most likely conclusion is that solar physics advances expand our understanding of the boundary conditions for small body behaviour, but don't fully explain 3I-ATLAS. Solar events modify the environment, but the object's response depends on its intrinsic properties: composition, structure, charge, reflectivity. Without knowing those properties, we can't definitively say whether solar activity matters. Speculative what if? What if 3I-ATLAS passed through a transient solar wind enhancement? A dense, slow-moving structure ejected from the sun, and the interaction produced drag or thrust that lasted for days. Solar wind structures can persist for tens of millions of kilometres, and an object moving through one might experience sustained forces. This is a stretch. The forces are weak, but combined with other mechanisms it might contribute. Solar physics teaches us that the heliosphere is dynamic, not static. Conditions vary with location, time, and solar activity level. 3I-ATLAS's journey through this environment is shaped by those variations. Understanding solar influences helps frame what's possible, even if it doesn't solve the mystery outright. Part 13. New findings in small body physics. Sample return or comet mission results. 2025. In September 2025, the Japan Aerospace Exploration Agency, JAXA, announced a stunning new wave of results from the extended analysis of samples returned by its Hayabusa 2 mission to asteroid Ryugu. While the spacecraft had brought its precious cargo back to Earth in late 2020, detailed laboratory study of the microscopic grains has continued for years, and the new results, published in Nature Astronomy, may have reshaped how scientists think about outgassing, surface evolution, and non-gravitational acceleration in small bodies. At first glance, Ryugu seemed well understood. A dark, carbonaceous, near-Earth asteroid, highly porous and loosely bound. A rubble pile more than a monolithic rock. But the 2025 findings revealed something deeper. Ryugu's grains are riddled with microscopic fractures, nanovoids and channels, forming a sponge-like internal structure. Embedded within are hydrated minerals and trace organics, signatures of past water alteration. What caught scientists off guard, however, was the behaviour of these grains under vacuum and heat. When exposed to simulated sunlight in laboratory conditions, the samples released gases steadily, even though they appeared dry. The process isn't explosive venting, like the classic image of comet jets erupting from a nucleus. Instead, it's diffusive outgassing, trapped volatiles, water molecules, carbon dioxide, nitrogen and other trace gases, slowly migrating out through a labyrinth of pores. The gas release is gentle, uniform and sustained, creating a continuous low-level thrust. Researchers estimated that, on an asteroid-sized body, this process could produce non-gravitational acceleration, detectable over days or weeks, yet without forming a visible coma or tail. That's where 3I-ATLAS enters the picture. If the interstellar object 3I-ATLAS has a similarly porous and volatile-rich structure, this mechanism could provide a natural explanation for its mysterious continuous in-plane acceleration, the one reported by NASA's JPL Horizons in November 2025. Unlike typical comets that vent through localized jets, producing visible plumes and asymmetric thrust, a diffusively venting body would thrust uniformly across its surface, generating a subtle, smooth acceleration, just as observed. This could also explain the absence of a detectable coma or tail. The gas might be escaping too uniformly and too faintly to scatter light or carry dust in detectable quantities. If the dominant volatiles are weak emitters such as nitrogen, argon or carbon monoxide, then even the most sensitive spectroscopic surveys might miss them. In short, 3I-ATLAS could be venting invisibly. However, this elegant theory still has problems. The A3 sub-zero condition in the JPL orbit solution, meaning there's no out-of-plane acceleration, remains a stubborn issue. Even with diffuse outgassing, a rotating body should show fluctuations in thrust direction unless its spin axis happens to align with its orbital plane, a rare coincidence. So, while the Hayabusa 2 findings expand the range of possible natural behaviours, they don't close the case. The geometry still matters, and so far the numbers don't line up perfectly. Still, the implications of Ryugu's gentle outgassing are enormous. It means that the boundary between asteroids and comets is blurrier than we thought. A body can appear inert and rock-like, yet still exhibit subliminal activity under solar heating. Over time, such subtle outflows could even alter an asteroid's trajectory, or, in an interstellar context, mimic controlled motion. Adding more context, the European Space Agency's Comet interceptor mission, scheduled for launch in the late 2020s, published a series of preparatory papers in 2025 detailing its strategies for studying pristine, long-period or interstellar visitors. Among these, a simulation study explored the phenomenon of microjets, narrow, intermittent plumes of gas and dust, too faint to be seen from Earth, but potentially capable of generating measurable thrust. According to those simulations, microjets could produce net accelerations on the order of 10^6 to 10^7 astronomical units per day squared, matching what's observed in 3I-ATLAS. Crucially, the jets could fire intermittently, modulated by sunlight and surface temperature, yet average out to a nearly steady acceleration if the object's rotation and orbital geometry aligned just right. From Earth's vantage, that would look exactly like a smooth, in-plane boost, the same signature baffling astronomers right now. The Comet interceptor studies also pointed out that surface microtexture, the distribution of cracks, pits, and granular slopes can drastically affect how sunlight is absorbed and re-emitted. A rough, fluffy surface can enhance localized heating and sublimation, even at large distances from the Sun. Combined with what we learned from Ryugu's porous structure, the picture that emerges is of small bodies as dynamic, living surfaces, continuously shaped by subtle physics invisible at telescope resolution. Meanwhile, complementary findings from NASA's OSIRIS-REx mission, which returned samples from asteroid Bennu in 2023, reinforce the same message. Analyses published in 2024 and 2025 showed that Bennu's regolith is similarly fragile and porous, with a mechanical strength lower than expected, more like compressed powder than solid rock. Such a structure could allow deep-seated volatiles to diffuse outward more easily than previously modelled. OSIRIS-REx also observed particle ejection events during its proximity operations around Bennu, where small grains spontaneously left the surface without identifiable vents. Put together, Hayabusa 2 and OSIRIS-REx have painted a new picture. Small bodies are not inert boulders, but complex quasi-active aggregates, capable of producing measurable accelerations without dramatic visual cues. For 3I-ATLAS, this offers a powerful analogy, though not proof, that its behaviour may belong to a continuum of natural processes that we are only beginning to quantify. Of course, speculation abounds. Could an interstellar body's microstructure differ even more radically? Travelling for millions of years through interstellar space, bombarded by cosmic rays and frozen beyond the heliopause, its surface might have become uniquely reactive. When such a body re-enters the solar system, sudden solar heating could activate trapped volatiles in unexpected ways, not unlike turning on a long-frozen battery. Some researchers have proposed that interstellar material could even contain exotic ices or amorphous carbon matrices unknown in typical comets, which could sublimate differently under solar radiation. Others take it further. In more speculative circles, the uniform acceleration and directional stability of 3I-ATLAS have revived the comparison to 1I Oumuamua, whose own non-gravitational acceleration in 2017 triggered debates about light sails, artificial probes, and exo-engineered materials. If 3I-ATLAS shares this invisible, steady thrusting but under a different structural model, porous venting instead of reflective pressure, it might suggest that multiple natural pathways can mimic propulsion. Or, as some whisper, it might hint at a deeper pattern among interstellar visitors that we still don't understand. The takeaway is both humbling and thrilling. The more precisely we measure, the more anomalies emerge. Hayabusa 2 and OSIRIS-REx have shown us that microscopic texture can change macroscopic motion. ESA's Comet interceptor aims to catch one of these bodies in the act, perhaps even an interstellar one, to see the invisible physics up close. And when that happens, it could tell us whether 3I-ATLAS's behaviour is the next chapter in natural small body evolution, or something that defies even that. In other words, the key to understanding a billion-ton mystery drifting between the stars might lie in a few milligrams of dust trapped inside a lab in Japan. Part 14, Frontier Physics, Dark Matter, / Modified Gravity, Hypotheses in Spacecraft-like Objects. We've explored natural mechanisms and even entertained the possibility of artificial structures, but there's another category of explanation that lives at the bleeding edge of physics, hypotheses that invoke forces or interactions we're only beginning to understand or haven't confirmed at all. These ideas require us to step outside the comfortable boundaries of established science and ask whether the universe contains phenomena that our current models miss entirely. Dark matter, modified gravity, exotic particles, heliospheric boundary effects. Each represents a frontier where observation outpaces theory and where the anomalies we observe might be signposts pointing toward new physics. Dark matter is one of the great unsolved puzzles of modern cosmology. We know it exists because galaxies rotate faster than visible matter alone can explain. Galaxy clusters hold together despite insufficient luminous mass. Gravitational lensing reveals mass where we see nothing. The evidence is overwhelming that about 85% of the matter in the universe is dark, interacting primarily through gravity, and possibly through forces we haven't detected. But what is it? Theoretical candidates include weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and more exotic options. Despite decades of searching, we haven't directly detected dark matter particles, which means we don't know how they behave at small scales or whether they interact with ordinary matter in subtle ways beyond gravity. Now here's the speculative leap. What if dark matter isn't uniformly distributed at the scale of the solar system? What if there are clumps, streams, or concentrations that objects can pass through? The Milky Way is thought to contain dark matter halos and substructure, remnants of smaller galaxies that merged with ours long ago. Some models predict dark matter streams threading through the galaxy, coherent flows of particles moving together. If the solar system is passing through such a stream, or if 3I-ATLAS entered the solar system along a trajectory that intersected a dark matter concentration, could that exert a drag force? The physics gets murky here because we don't know how dark matter couples to ordinary matter beyond gravity. If dark matter particles scatter off atoms or nuclei, even very rarely they could transfer momentum. A body moving through a dark matter cloud would experience drag, a force opposing its motion. But the cross-section for such interactions, if they exist at all, is constrained by experiments to be extraordinarily small. Dark matter is dark precisely because it doesn't interact strongly. Producing a force of 10 to the negative sixth astronomical units per day squared on a body with mass in the millions of kilograms would require dark matter densities far higher than anything predicted or observed in our galactic neighbourhood. Let's quantify this. The local dark matter density near the Sun is estimated at about 0.3 giga-electron-volts per cubic centimetre, equivalent to roughly 100,000 times lower density than the interstellar gas. If dark matter particles have masses around 100 giga-electron-volts and scatter off nuclei with cross-sections near current experimental limits, the drag force on a kilometre-sized object would be utterly negligible, many orders of magnitude below what we need to explain 3I-ATLAS. To get meaningful drag, you'd need either much higher dark matter density, much larger scattering cross-sections, or some amplification mechanism. None of these are supported by current evidence. But what if dark matter interacts through a fifth force, something beyond gravity and the standard model interactions? Some theories propose that dark matter couples to ordinary matter via new bosons or through portals involving Higgs-like fields. If such a force exists and operates at ranges of astronomical units, objects moving through dark matter fields could experience accelerations. The challenge is that these forces must be extremely weak to have avoided detection in laboratory experiments and solar system dynamics up to now, yet strong enough to affect 3I-ATLAS. Threading that needle requires very specific, contrived parameters. Another frontier hypothesis involves modified Newtonian dynamics, or MOND, and its relativistic extensions like modified gravity theories. MOND was originally proposed to explain galaxy rotation curves without invoking dark matter, by positing that gravity behaves differently at very low accelerations. In the MOND framework, when accelerations fall below a critical threshold around 10 to the negative 10th meters per second squared, gravitational attraction becomes stronger than Newton's inverse square law predicts. This threshold is close to the accelerations experienced at the edges of galaxies, which is why MOND works well there. Could MOND or related theories apply to 3I-ATLAS? The object's acceleration is about 10 to the negative sixth astronomical units per day squared, which converts to roughly 10 to the negative 8th meters per second squared. That's higher than the MOND threshold, but in a regime where modified gravity effects might still be relevant depending on the specific theory. If gravity transitions smoothly rather than sharply at the threshold, there could be residual corrections that produce anomalous accelerations. The problem is that MOND and its variants are designed to explain phenomena at galactic scales, not within individual solar systems. Within the solar system, Newtonian gravity plus general relativity work exquisitely well. Spacecraft trajectories, planetary orbits, even the precession of Mercury's orbit, all match predictions to extraordinary precision. Invoking modified gravity to explain a single small body's motion requires that the modification is somehow sensitive to properties of that body, its composition, charge, or origin, that don't affect planets or normal asteroids. That's a tall order, and would represent a major departure from the universality of gravity that underpins physics. A related idea involves the heliosphere boundary and interactions at the edge of the Sun's influence. The heliosphere is the bubble of solar wind and magnetic fields surrounding the solar system, extending roughly 100 astronomical units in the direction of the Sun's motion through the galaxy and less in other directions. At the heliopause, the boundary where solar wind pressure balances interstellar medium pressure, conditions change abruptly. Charged particle densities shift, magnetic field orientations flip, and the environment transitions from solar-dominated to galactic-dominated. 3I-ATLAS, as an interstellar object, presumably passed through the heliopause on its way into the solar system. Could crossing that boundary have imparted a charge, magnetic moment, or other property that now causes it to interact anomalously with the solar wind or heliospheric magnetic field? This is plausible in principle, The heliopause is a complex region where particles are accelerated, fields reconnect, and shocks form. Objects transiting this zone might be altered, acquiring surface charges or embedded magnetic fields. However, even if 3I-ATLAS became charged or magnetized at the heliopause, the forces it experiences from the solar wind in the inner solar system depend on the magnitude of that charge or magnetization and on the local solar wind conditions. As discussed earlier, typical solar wind forces are far too weak to explain the observed acceleration. You'd need extreme charging, perhaps the object acting as a giant capacitor, or unusual magnetic properties that couple strongly to the interplanetary field. There's no observational evidence for such properties, and invoking them without independent confirmation feels like adding epicycles. Galactic cosmic rays, high-energy particles from supernovae and other violent events across the galaxy, permeate the heliosphere. Their flux varies with solar activity. The solar wind modulates them, reducing their density near the Sun. Could cosmic rays interact with 3I-ATLAS in a way that produces thrust? If the object has superconducting materials or unusual electromagnetic properties, it might channel or reflect cosmic rays asymmetrically, creating a net force. This is wildly speculative, requiring materials and structures we've never observed in nature. Then there's the idea of an interstellar wind of exotic particles. What if there's a population of not yet detected particles? Not dark matter, but something else. Perhaps sterile neutrinos with slightly different properties, or hypothetical particles from extensions of the Standard Model that stream through the galaxy. If these particles interact with matter more strongly than dark matter, but are rare enough to have escaped detection, a body passing through a stream of them could experience drag or thrust. The parameters would have to be finely tuned, common enough to affect 3I-ATLAS over 20 days, rare enough not to show up in other observations, and interacting just strongly enough to produce the measured acceleration without other consequences. All of these frontier physics hypotheses share a common feature. They require new, unconfirmed physics to work. They're not extensions of well-tested theories, but speculative additions to our understanding of the universe. That doesn't make them wrong. Science advances by proposing and testing new ideas, but it places them in a different category from natural or even artificial explanations. Natural explanations rely on known physics applied in novel ways. Artificial explanations invoke known engineering scaled up or applied by others. Frontier physics explanations invoke unknown mechanisms, which makes them harder to test and easier to manipulate to fit any anomaly. That said, history shows that anomalies sometimes do point to new physics. The precession of Mercury's orbit was an anomaly that Newtonian gravity couldn't fully explain, and it led to general relativity. The rotation curves of galaxies were anomalies that led to the dark matter hypothesis. The accelerating expansion of the universe was an anomaly that led to dark energy. Not every anomaly is a breakthrough. Most turn out to be measurement errors or misunderstandings of known effects, but some are real. The question is how to distinguish them. For 3I-ATLAS, the pathway to validating a frontier physics hypothesis would require multiple lines of evidence. First, the anomaly must persist and strengthen with better data, ruling out observational artifacts. Second, the proposed mechanism must make testable predictions beyond just explaining 3I-ATLAS. For example, if dark matter drag is real, other small bodies in similar regions should show similar effects. If heliospheric interactions produce the thrust, we should see correlations with solar wind conditions or be able to reproduce the effect in laboratory simulations. Third, independent experiments or observations must confirm the underlying physics, detecting dark matter interactions, measuring modified gravity at relevant scales, or finding the exotic particles proposed. None of these steps have been taken for 3I-ATLAS. The frontier physics explanations remain conceptual, frameworks for thinking about possibilities rather than established theories. They're valuable as intellectual exercises, pushing us to question assumptions and explore the edges of knowledge. But they shouldn't be mistaken for answers. There's also a psychological dimension to frontier physics explanations. They're appealing because they're exotic and transformative. If 3I-ATLAS is evidence of new physics, that's exciting, a discovery that reshapes our understanding. The temptation is to leap to such explanations prematurely, to prefer the revolutionary over the mundane. Science requires us to resist that temptation, to exhaust conventional explanations first, and to demand rigorous proof before accepting radical new ideas. Yet we also can't be so conservative that that we ignore genuine signals of new physics. The balance is difficult. In the case of 3I-ATLAS, the data is anomalous enough to warrant serious investigation, including exploration of unconventional ideas. But it's not yet compelling enough to overturn established physics or to justify building new theories around a single object. Perhaps the most honest position is to say, frontier physics hypotheses for 3I-ATLAS are currently very low probability, but they highlight the limits of our knowledge and the possibility that the universe contains surprises. If 3I-ATLAS's behaviour remains unexplained after exhaustive investigation of natural and artificial mechanisms, and if similar anomalies accumulate in other objects or systems, then revisiting these frontier ideas becomes more justified. Until then, they serve as reminders that science is never complete, that what we don't know still vastly exceeds what we do, and that maintaining intellectual openness is as important as maintaining skepticism. The interplay between established physics and frontier speculation defines the scientific method. We build on solid foundations but remain alert for cracks, anomalies that don't fit, and that might signal something deeper. 3I-ATLAS is such an anomaly. Whether it cracks the foundation, or turns out to be a quirk of an unusual but ultimately natural object remains to be seen. But asking the questions, entertaining even the unlikely possibilities, and designing observations to test them is how science advances. In our final part, we'll bring all this together for a forward look and viewer takeaway, mapping what to watch in the next 12 months and what it all means. Part 15, Synthesis and Forward Look. What to watch in the next 12 months. We've travelled a long road together, from the initial anomaly of 3I-ATLAS's unexplained thrust to the natural hypotheses that strain under scrutiny, from exotic possibilities of sails and propulsion to frontier physics at the edge of knowledge. We've placed this object in the context of other interstellar visitors, examined the roiling energy environment of our solar system, and explored the social dynamics that shape how science interprets anomalies. Now it's time to step back, take stock of what we know and what we don't, and look ahead to the observations and discoveries that might resolve this mystery or deepen it. Let's start with what we know with reasonable confidence. 3I-ATLAS is moving through the inner solar system on a hyperbolic trajectory consistent with interstellar origin. It's displaying non-gravitational acceleration characterized by radial and tangential thrust components, A1 and A2, while showing zero measurable out-of-plane acceleration, A3 equals 0. This acceleration has been sustained over approximately 20 days, producing a velocity change of about 60 meters per second. Observationally, the object appears as a faint point of light with magnitude around 14.7 to 14.9, showing no significant brightness variations and no clearly resolved coma, tail, or jets in public imaging. Spectroscopic observations, if available, have not reported strong emission lines from typical cometary volatiles like water vapour or carbon monoxide. Now let's enumerate what we don't know, and this list is longer and more consequential. We don't know the nuclear size or shape of 3I-ATLAS. Without resolved imaging, we can only estimate based on brightness and assumed albedo, and albedo itself is unknown. A dark object looks faint for its size. A bright reflective object looks faint because it's small. The range of possible sizes spans orders of magnitude. We don't know the mass. Without size and density, mass is unconstrained, and mass matters critically for calculating what forces are needed to produce the observed acceleration. We don't know the surface composition, what ices or minerals cover the nucleus, what volatiles it contains, or how reflective it is across different wavelengths. We don't know the spin state, how fast it's rotating, what its rotation axis orientation is, or whether it's tumbling chaotically or spinning steadily. We don't know its thermal properties, how efficiently it absorbs and radiates heat, or how heat conducts through its interior. And we don't know its origin story, what stellar system it came from, how long it's been wandering the galaxy, or what environment it formed in. Each of these unknowns limits our ability to choose between hypotheses. A small, highly reflective object fits the sail hypothesis beautifully, but would be implausible as a natural comet. A large, porous, volatile, rich object fits natural outgassing better, but struggles with the lack of visible coma. A dense, rocky body with embedded volatiles might explain invisible venting, but raises questions about how it retains ice. An object with unusual composition, rich in carbon monoxide or nitrogen, might produce high-velocity gas jets that escape detection, but should still show spectral signatures. Until we constrain these properties, we're building models on sand. So what should we watch in the next 12 months? First and foremost, orbital updates. NASA's Jet Propulsion Laboratory Horizon system continuously refines solutions as new astrometric observations come in. If 3I-ATLAS's trajectory changes, if the non-gravitational parameters shift, if A3 remains zero or suddenly becomes non-zero, those changes would be diagnostic. A shift from planar to three-dimensional thrust would suggest changing outgassing geometry, perhaps as different regions of the nucleus rotate into sunlight. Sustained planar thrust strengthens the case for either precise geometric alignment or active control. Trajectory changes that look like deliberate maneuvers, sudden velocity adjustments that align with specific objectives, would be extraordinary evidence favouring the propulsion hypothesis. Second, telescope campaigns. Several major observatories have time allocated or could propose observations of 3I-ATLAS. The James Webb Space Telescope, with its infrared sensitivity, could detect thermal emission from the nucleus, constraining size and temperature. It could also search for faint molecular emissions in the infrared that ground-based telescopes miss, gases like carbon monoxide, methane, or carbon dioxide that sublimate efficiently, but emit weakly in visible wavelengths. Large ground-based telescopes with adaptive optics, like the Keck telescopes in Hawaii, or the Very Large Telescope in Chile, could attempt resolved imaging, trying to see the nucleus as more than a point, searching for coma structure, jets, or elongation that might hint at shape or activity. Spectroscopy across ultraviolet, visible and infrared wavelengths would build a comprehensive picture of what 3I-ATLAS is made of and whether it's venting. Third, photometric monitoring. Continued brightness measurements over months can reveal rotation periods through light curve variations, constrain albedo by comparing brightness at different phase angles, and detect any changes in activity level. If 3I-ATLAS suddenly brightens, that could signal a new outburst, delayed venting triggered by subsurface warming or fragmentation. If it fades faster than expected, that might indicate a change in reflectivity or orientation, relevant for assessing the sail hypothesis. Fourth, radar observations. Planetary radar systems like the Goldstone Solar System radar in California, or the Arecibo telescope before its collapse, were used to observe asteroids and comets, providing direct measurements of size, shape, spin, and surface roughness. Goldstone remains operational and could potentially detect 3I-ATLAS if it comes close enough and is large enough to return a signal. Radar would decisively constrain size and would reveal whether the object is elongated, spherical, or irregular, information critical for distinguishing hypotheses. Fifth, AI-driven surveys and archival searches. As discussed in Part 11, machine learning algorithms are combing through archival data from sky surveys looking for anomalies. It's possible that 3I-ATLAS was imaged months or years ago during its inbound journey, but the observations weren't recognised or flagged. Recovering pre-covery images would extend the observational arc, improving orbital solutions and potentially showing whether the non-gravitational acceleration started gradually or suddenly. AI might also discover similar objects in ongoing surveys, and the existence of a population would reframe everything. If 3I-ATLAS is one of many, we're looking at a class phenomenon, not a unique event. Sixth, solar and heliospheric monitoring. Tracking solar activity, flares, coronal mass ejections, solar wind conditions, and their timing relative to any changes in 3I-ATLAS's behaviour could reveal correlations. If the object's acceleration strengthens or weakens in response to solar events, that suggests environmental coupling. If it's independent of solar variations, that argues for intrinsic mechanisms, either venting or propulsion driven by internal processes. Seventh, theoretical developments. Papers are undoubtedly being written right now, modelling different scenarios, testing whether particular compositions or structures can reproduce the observations. Publications in journals like Nature, Science, the Astrophysical Journal, or Icarus will present competing interpretations, and the community will debate them. Consensus might emerge, or the debate might remain unresolved, but the theoretical work will sharpen our understanding of what's possible and what's implausible. Eighth, mission proposals. It's unlikely but not impossible that space agencies could fast-track a mission to intercept or observe 3I-ATLAS more closely. Interstellar objects move quickly and are hard to reach, but if 3I-ATLAS is deemed sufficiently important, A flyby mission using existing spacecraft or a rapid response probe could be proposed. The European Space Agency's Comet interceptor mission is designed for such opportunities, though it won't launch until the late 2020s. Still, the possibility of close-up observation, even from a small CubeSat, would provide definitive answers. Now let's game out possible scenarios for how this resolves over the next year. Scenario A. Natural explanation confirmed. High-resolution imaging or spectroscopy detects a faint coma or jets that were previously below detection thresholds. The jets are found to be aligned in such a way, due to the nucleus's spin and shape, that they produce net thrust confined to the orbital plane. The composition is revealed to be rich in supervolatiles like carbon monoxide, explaining the high-velocity venting and low dust production. A detailed model incorporating all these factors reproduces the observed acceleration, and the mystery is solved. 3I-ATLAS becomes a spectacular example of an unusual but ultimately natural interstellar comet, and we learn that our assumptions about cometary behaviour were too narrow. The object enriches our understanding but doesn't revolutionize it. Scenario B. Exotic explanation gains credence. Photometric observations across multiple wavelengths reveal an unusually high albedo, approaching 90 or 100%, far higher than any natural comet. Phase curve analysis shows that 3I-ATLAS reflects light like a smooth, flat surface, not a rough, irregular rock. Thermal measurements indicate very low mass, implying extremely low density inconsistent with solid ice or rock. Together, these findings point to a thin, lightweight structure, a sail. The scientific community debates whether such a structure could form naturally, perhaps as a frozen sheet of volatiles in interstellar space, or whether it's engineered. No consensus emerges immediately, but the sail hypothesis becomes the leading explanation, opening a new chapter in the study of interstellar objects and raising profound questions about whether we're looking at technology, ours or someone else's, adrift between the stars. Scenario C. No decisive resolution. Additional observations improve constraints but don't definitively favour any hypothesis. The coma remains absent or barely detectable. Albedo measurements are inconclusive. Non-gravitational parameters stay puzzling. 3I-ATLAS fades as it exits the inner solar system, becoming too faint for detailed study. The object remains a mystery, filed away as an anomaly that couldn't be explained with available data. Years later, when better instruments or more examples emerge, scientists revisit 3I-ATLAS, but in the near term it's an unsolved puzzle, a frustrating reminder of the limits of current observational capabilities. Each scenario has different implications. Scenario A, the natural resolution, would be the most scientifically satisfying in some ways, demonstrating that nature is stranger and more diverse than we realised, but that our physical models are fundamentally sound. It would encourage observers to look more carefully at future interstellar objects, to not assume comets vent visibly, and to expect the unexpected. Scenario B, the exotic resolution, would be transformative. If 3I-ATLAS is a sail, whether natural or artificial, it forces us to expand our thinking about what exists in the galaxy, about how matter structures itself on large scales, and possibly about whether intelligence is rare or common. The implications ripple outward into philosophy, astrobiology, and technology. Scenario C, the unresolved mystery, is the least satisfying but perhaps the most realistic. Science often moves slowly, constrained by resources, technology, and the sheer difficulty of observing distant, faint objects. Not every question gets answered immediately, and some remain open for decades. Beyond the immediate resolution, 3I-ATLAS raises broader questions about how we search for and interpret anomalies. This object was noticed because our monitoring systems are good enough to detect small deviations from gravitational orbits, and because the astronomical community is alert to interstellar visitors. But how many anomalies do we miss? How many objects pass through unnoticed because they're faint, or because their behaviour is subtle, or because we don't look in the right wavelengths? The answer is undoubtedly many. The sky is vast, our surveys cover only fractions of it at any given time, and small bodies are hard to track. Improving our detection capabilities, building larger telescopes, deploying more sensitive instruments, and applying AI to sift through data all expand our reach. Each improvement raises the probability that we'll find more objects like 3I-ATLAS, or stranger ones. And with each discovery, our taxonomy of what's normal expands. What seemed impossible becomes possible. What seemed unique becomes part of a pattern. This is the trajectory of science, moving from ignorance to partial knowledge to deeper understanding, always provisional, always ready to update when new evidence arrives. There's also a meta-level question about how science handles the extraordinary. When faced with an anomaly that challenges assumptions, how do we balance skepticism and openness? Too much skepticism, and we dismiss genuine discoveries prematurely. Too much openness, and we waste time on false leads and pseudoscience. The peer review process, public debate, and replication of results are safeguards, but they're imperfect. Careers, funding, and reputations are on the line, creating social pressures that can distort objectivity. 3I-ATLAS tests these dynamics. The natural hypotheses are the safe bet, the explanations that fit within existing frameworks, and that the community is predisposed to accept. The exotic hypotheses are riskier, requiring more evidence and facing higher barriers to publication. The frontier physics hypotheses are riskiest of all, invoking new mechanisms that most scientists consider unlikely. Yet all three categories deserve consideration, evaluated on their merits against the data. The challenge is maintaining that balance, neither prematurely dismissing ideas nor uncritically accepting them. For those of us watching from outside the scientific community, 3I-ATLAS is a reminder that the universe is full of surprises, that our knowledge is incomplete, and that the boundaries of the known are where the most interesting discoveries happen. It's also a reminder that science is a human endeavour, shaped by the people who practice it, with all the creativity, bias, passion and limitation that entails. We should celebrate the progress science makes while recognising its imperfections. So as we close this exploration, here's the question to carry forward. Are we watching not just a comet, but a signal? A signal of something new walking into our solar backyard, something that doesn't fit our categories, something that forces us to think bigger and stranger. Maybe 3I-ATLAS is just a comet, an unusual one but ultimately natural. Maybe it's something else, a sail, a probe, a fragment of alien engineering, or a manifestation of physics we haven't grasped yet. The data doesn't yet tell us which, but the fact that we're asking these questions, seriously and rigorously, is itself significant. The next 12 months will bring new observations, new analyses, and new debates. Stay tuned. Follow the updates from JPL Horizons. Watch for papers from researchers studying 3I-ATLAS. Listen to the discussions in the astronomical community. The story is still being written, and you're witnessing it unfold in real time. Science at its best is a collective human effort to understand reality, and mysteries like 3I-ATLAS are why that effort matters. We stand at the threshold, looking out at a visitor from the stars trying to read its secrets. It accelerates silently through the dark, confounding our expectations, whispering that the cosmos holds more than we imagined. Whether it's a cosmic quirk or a cosmic message, time and observation will tell, but for now we watch, we wonder, and we wait, knowing that the universe has surprised us before and will surprise us again, and that each surprise brings us one step closer to understanding our place in the infinite expanse. The anomaly of 3I-ATLAS isn't just a scientific puzzle, it's an invitation to look harder, think deeper, and remain humble before the vastness of what we don't yet know, and that, in the end, might be the most important lesson of all.